Okay, so let us resume our discussion on the three types of property specifications. We were looking at assert properties, assume properties and cover properties. So, let us go into an example to see what the assert and assume properties mean. So, let us say that we have this property to check on the memory arbiter. This is the same arbiter as we had been discussing before, right, our previous example. It says every low priority request R2 is eventually granted by the arbiter. We want to add this property. So, we write this as property no starvation at passage clock R2 implies sometime in the future G2. Now, the problem is that this property conflicts with our earlier property P1. Remember what P1 was? P1 was that whenever the high priority request comes, then for the next 2 cycles grant must be asserted, right. Now, why does this conflict with this? Because
G1 has to be high for 2 cycles and there G2 can be high in the second cycle.
no, but this one only says that G2 has to be high sometime in the future.
It should be in the second cycle.
No, sometime means any time in the future. If you can satisfy G2 any time in the future, say 3rd cycle, 4th cycle, then also this property is all right. This one just says that sometime in the future G2 must be true, sometime, right. But there is still a conflict between these two. First of all, do you see what is the conflict? Right. R1 can be high forever, right. If R1 is high forever, then this property will imply that G1 has to be high forever, right. But if G1 is high forever, then we cannot assert G2 anywhere in future. If G1 is high forever, then nowhere in the future can G2 be asserted, because G1 and G2 cannot be asserted together by virtue of the mutex property. So, we cannot satisfy these two together, because additionally we have the mutex property. So, the 3 of them cannot be satisfied together. But then let us understand that why are we having this conflict? Because we are having this conflict under the scenario that R1 is asserted either continuously or at least once in every 2 cycles, right. But then if we say that if we assume that R1 is not going to behave like that, if we are given that R1 is not going to behave like that, then we can check this property on the arbiter. Now, understand the situation. In general, if you give these 2 properties, there is a conflict. But we may know that for our system, R1 will not be asserted forever. We may know that. This is our understanding of the context in which this arbiter is being used. So, this assumption is coming from the rest of the world. It is coming from all those devices which request the memory arbiter, right. So, that is the assumption. We are given that whenever G1 is asserted, R1 remains low for the next 4 cycles. This is given to us. This is not a property of the arbiter. This is a property of the device which drives R1, right. That device which drives R1 keeps R1 low for 4 cycles whenever it gets a grant, right. So, that property is written like this. It is written like any other property, that at passage clock G1 implies not R1 for the next 4 cycles. This is a repetition operator. Remember, what does the repetition operator says? It says not R1 for 4 consecutive cycles, right. Now, see, these two are things that we want to check on the arbiter. This is not something that we want to check on the arbiter. This is the assumption that we have about the environment of the arbiter, right. So, we are going to write it like this. We are going to write this and declare it as an assume property. So, see, this is the important line. We are saying assume R1 is fair colon assume property fairness of R1, right. Remember, in one of the earlier slides I had shown you that after declaring the property, after defining the property, you define it as an assert property. When we, this definition was there in the interface definition. In one of the earlier slides I had shown that in the interface definition we use these lines. So, now in the interface definition we are going to define this one as an assume property and this one as an assert property. Okay. This is the syntax of SVM. Now, under the assumption assume R1 is fair, there is no conflict between properties grant when request and assert no starvation. There is no conflict between grant when request was this property, this one, and assert no starvation, there is no conflict now, right. Do you see that there is no conflict now by virtue of this assumption? Both assume and assert properties may use input and output variables of the DUT. So, you can see that here this was an assumption, but then G1 is an output of the DUT, R1 is an input of the DUT. Right. So, it is not the case that assume properties must be only on the environment variables, that it should be only on the inputs, not necessary, right. Assume properties are not related to any specific assert property, they are generic assumptions about behaviors. So, it is not that these two are a pair, it is not that that there is any implication between this and this, if this then this, nothing like that. This assumption is a generic assumption, it says that the inputs or the input output behavior is always going to satisfy this, we are given that, right, we are given that this property holds, right. So, and that it is given is regardless of what we want to check on the arbiter. So, there is no relation between the assume property and the assert property. In dynamic assertion verification, what is going to happen? When the simulation is taking place, the assume property will be monitored, the assert property will also be monitored, right. Now, suppose the assume property fails, what does that mean? The test bench has driven some scenario which was not expected, right. If it violates an assumption, if the simulation trace violates an assumption, that means that the simulation has driven a trace which was not supposed to come, right. That can be again because of two reasons. One is that the test bench is incorrect, or it could be that your assumption was too strict and the test bench designer is correct in driving that scenario. You wrote a very strict assumption and then it shows that that assumption was too strict and there can actually be a scenario which violates the assumption, right. So, we have to go back and decide which of these two is the case, and then accordingly either weaken the assumption or correct the test bench, right. But in both cases, if the assumption fails, there is no point in checking the assertion. Why? Because the assertions are to be guaranteed only under those scenarios where the assumptions hold, right. So, if in the simulation trace your assumption fails, you can abort the checking of the assertions.
But what if we have two assumptions, like two properties, then if one of them fails, then we will not check the assertions?
No, because you see, as I mentioned just now, assumptions are generic behavioral constraints. They have got nothing to do with any specific assertions. So, if any assumption fails, it means that you are driving something which is not going to appear in practice. So, you will first say that this must be an invalid scenario that is being driven. So, what is the point in checking the assertions? None of the assertions should be checked, regardless of whether they share the same variables or not. There is no point checking it, right. Now, what happens in formal property verification? In formal property verification, if we do not have assumptions, we will create the state space of the design under test. In other words, we will create the state machine of the design under test and then check whether the property holds on that state machine, right. Now, suppose where is the assumption coming in here? Now, remember that if you have a state machine which has both inputs and outputs, right, then how can you, where is the source of non-determinism? First of all, we need to understand that in a state machine which reacts to the environment. So, it has present state, input, next state. Where is the source of non-determinism? If we now want to model that state machine as a Kripke structure, remember Kripke structure did not have any inputs, it did not have any inputs. So, how can we convert a finite state machine which has inputs to a Kripke structure? So, what we do there is we treat the input variables as additional state variables. We treat the input variables like additional state variables, right. So, in a normal finite state machine, we have present state bits, we have input bits, okay. Let us call them present input bits, and then we have next state bits, right. This is the typical transition relation for a finite state machine, right, and then you have your vectors here, the truth table here. Now, what we are saying is that let us say that we have the present state, let us say that from the present state 0 0, on getting 1 I was going to 0 1, right. Now, what we do is we transform that to present state, present input, next state, next input, and say that this whole thing is my present state and this whole thing is my next state, right. In a Kripke structure, there is nothing called inputs. So, this is the present state, this is the next state. So, what are we going to do about this? So, we have 0 0, and then when I get 1, the next state is 0 1, right. What is the next input? Could be 0, could be 1, right. So, we have one entry like this and we have another entry which is present state 0, next state is 0 1, this is 1, right. Now, if you look at this, so did you see what happened? We basically, this entry in the traditional truth table got split up into 2 entries because the next input is not known. So, it could be 0 or 1, right. So, here this was a transition from 0 0 to 0 1 on the input 1, right. What we have transformed that is in a transition from 0 0 1 to 0 1 0 0 1 1. That is what we have done. This transition 0 0 1 to 0 1 0, this transition is this one, and this transition is this one. See, 0 0 1 to 0 1 1. Is that clear? So, this is the transformation that we use to transform a finite state machine having inputs to a Kripke structure, right. Now, you see that what we have is a state machine which has no inputs, but it is non-deterministic, right. See, here it was non-deterministic. There is this state from which it makes non-deterministic transitions to any of these two states. Now, given this non-deterministic state machine, which is our Kripke structure, any assumed property is specifying what? It is specifying that certain paths in that Kripke structure will not actually be traced, right. So, if you look at this assumption, it says that paths where R1 is asserted forever will not be traced, because that is violating this assumption, right. So, in that Kripke structure, all those paths that you have where you are having R1 forever, you know that those paths are actually fictitious paths in the state machine. There, in practice they will not be there. That is what your assumption is telling you, right. And then you can use that to prune out those paths. All the time you may not be able to do so, because pruning out paths, pruning out one path does not prune out the state, and things will start dropping off if certain transitions or certain states can be totally eliminated, right. So, using assumptions may not always reduce the size of the state machine, but in many cases it does, right. So, this is what assumed properties are used for in formal verification. They are used to prune the state space before checking the assert properties. We are going to look at actual examples later on when we talk about model checking to see how this is affected. Now, we come to cover properties. Cover properties can be declared like this, that suppose we want to check this property, that whenever R1 is asserted for 2 cycles, then in the next cycle, whenever R1 is not asserted for 2 cycles, then in the next cycle G1 is also not asserted, right. Now, this property is interpreted non-vacuously when R1 is low in 2 consecutive cycles. In all other runs, the property becomes vacuously true. So, we write this as a cover property like this, just like we defined assumed properties etc., we can write it as a cover property. Now, coverage results are divided into 2 things. One is coverage for properties and coverage for sequences, and the results that are displayed by, see, this is the results that must be displayed for any system Verilog compliant simulator. It should display the number of times the property was attempted the number of times it matched, the number of times it failed, the number of times it succeeded because it vacuously succeeded, each attempt with the attempt ID and time, right. So, every time it starts matching the property, it assigns an attempt ID with it, and there is a time at which you start the matching, right. Each success or failure with an attempt ID and time. So, this is the complete coverage report that will come out when you declare a property as a cover property, right. Another thing that we must look into is that the vacuity that is looked at here is only implication vacuity, in the sense that all that it does is that it looks at the implication operator, and the antecedent of that implication operator, whenever that matches, we say that this property matches non-vacuously, right. But see, you know that any implication can also be written in terms of logical operations, like A implies B can be written as not A or B, right. So, if you can rewrite the properties without using the implication operator, and then it is not going to check for vacuity at all, right. So, it is a sort of naive way of checking for vacuity, in the sense that it just looks at the antecedent of the implication, and whenever that matches, it says that we have a non-vacuous match, right. But that is what system Verilog assertion supports, right. So, we can, there are methods for vacuity checking which are much better than this, but they are not part of the standards. In system Verilog, you also have multiple clock support. So, you can have concatenation of two sequences where each sequence can have a different clock. So, you can write a sequence expression like this, that at passage clock, I think this should be property. Please read this as property S1 and then property. At passage clock 0, 60 #1, this is another typo here. You can write at passage clock 1 sig 1. So, you see that this sequence will be evaluated with this clock, and this sequence will be evaluated with this clock. So, if this sequence has some #1, then that is going to be interpreted with this clock, and if this sequence has some #1, then it is going to be interpreted with this clock, right. Then you can also have the antecedent having one clock definition and the consequent having another clock definition, that is also permitted, right. So, this is just another thing that you know, that clock, the definition of clock is part of the property specification. In fact, your clock may not be an actual clock, it could be some signal A. So, always at A. So, that would mean that whenever A changes, so if you write at A some property is being checked, that whenever A changes, then you start matching that property, right. You can put any arbitrary event there. Now, we are going to look at the styles for writing assertion IPs. Assertion IPs are property suites. When you have a specification and you want to build a set of properties for that particular specification, then the set of properties that you write is called an assertion IP. And assertion IPs for most of the standard protocols are today available in the market. So, you have assertion IPs for the ARM AMBA protocol suite, which is the ARM processor buses protocol. Then you have the protocol suites for PCI, then you have it for PCI Express, which is the new protocol that is followed by the new Intel processors. Then you have hyper transport, there is the Ethernet protocol, the Wi-Fi, and all these for all these protocols there are assertion IPs. These assertion IPs have been built by companies studying the specification document for these. For many of these there are IEEE standards for the protocol specifications. So, they take that protocol specifications and write down the properties, and the properties are sold. So, for example, if TI wants to use Ethernet interface on one of their chips and they want to verify whether the interface is behaving correctly, they can buy an Ethernet assertion IP and then simply plug it with their design, and then when they run simulation those properties are being checked. And remember that everything is bound with the design under test through an interface. So, the name mapping between the signal names used in the assertion IP and the signal names used in the circuit is done through that interface. So, by virtue of that your assertion IP can use any signal names and your actual circuit can use other signal names, but you can bind them together, right. So, that is how assertion IPs are bought off the shelf and plugged into the design, and the verification process just uses those assertions. So, we are going to look at some of the challenges in writing these assertion IPs. So, one style of writing assertion IPs is using event based specifications. So, where only properties are defined over interface signals, and we are also going to look at state based specifications, where we will first define things called auxiliary state machines, and then the properties will use the state bits of those auxiliary state machine, right. So, as soon as we see examples it will become clear. So, we are going to study this with respect to a simple bus protocol which we will call the MyBus protocol. So, in this protocol we are looking at the interface of a master device. The master device has access to the bus. The bus is a multiplex bus. So, it can float both data and address, but not in the same cycle. So, the same bus is used to float the address and also the data at selected cycles. Okay. The master makes a request to the arbiter, it gets a grant from the arbiter. Okay. To start a transaction, the master asserts request, waits for grant, and then when it gets the grant its address cycle begins. What does it do in the address cycle? It floats the address on the bus and waits for the ready signal from the slave, right. And when the slave produces the ready signal, it goes into the data cycle, and on data cycle, on receiving the ready signal, it expects data in the next cycle if it is a read transaction, or the master will float the data in the next cycle if it is a write transaction. If the master is writing, then immediately on getting ready it will float the data on the data bus on the bus, and if it is a read transaction, then as soon as it gets ready it will expect that the data is available in the bus, right. The RW signal indicates whether it is a read transaction or a write transaction. After each data cycle the master may start another address cycle by floating the next address, right. So, let us say that this is the simple protocol that it follows. So, a simple transfer looks like this, that see request is raised first, and then let us say the arbiter gives the grant in the next cycle. Okay. As soon as it gets the grant, it floats the address, right. The address is floated, and then it waits for the slave to be ready. In the next cycle the slave was not ready, so it keeps the address floated for the next cycle also, and then when it gets ready, it lowers, it immediately floats the data, right. It floats the data, and then again in the next cycle it can float another address, and if the slave is ready then it floats the data, right, and so on. So, see the ready goes up and down, it asserts ready, whenever it gets the data it lowers it, again it asserts it in the next cycle if it is ready, and so on, right. Is that clear? Right. So, this is a simple transaction. Suppose we want to write these properties. The first property says that the protocol is non-preemptive. Once granted, the master owns the bus until it lowers its request line, right. So, we will see how to code this property. The second property says that if the master is in the address cycle, it should not change the address floated in the bus until it receives the ready signal from the slave. And the third property says each data cycle is of unit cycle duration, right. Now, let us try to code this in SVA. First one says that once granted, the master owns the bus until it lowers its request line. So, we say, okay, there is a new construct which I did not mention before. $rows grant means this becomes true, this part becomes true in a cycle if the signal grant rose in that cycle. So, in other words, in the previous cycle grant was low, in this cycle grant is high, then $rows grant is true. Is that clear? It is like passage grant. Then, so if grant was raised, then grant will remain high. So, this is a repetition operator. We must have grant until we get not request. So, grant rose implies grant will remain high until request is lowered. So, that is non-preemption, that as long as your request is high, grant cannot be taken away from you. Clear? Yes or no? Now, let us look at this thing. This is where the problem will start coming in. If the master is in the address cycle, remember what is the address cycle? You assert the request, get the grant, and as soon as you get the grant, your address cycle starts. If the master is in the address cycle, it should not change the address floated in the bus until it receives the ready signal from the slave. If the slave is not ready, then the address should be held. Now, suppose we write it like this. So, I have already indicated that this property is not correct. So, incorrect address table. Now, let us see what we write here. We are writing int x. So, here we are using a local variable. At passage clock, request and grant and not ready, okay, request and grant and not ready, and if the address floated is x, then in the next cycle also the address floated must be x. So, here you see x is being assigned, here x is being checked. So, whatever was the address here must be the address here, right, that is what it is checking. Under what condition? Request and grant and not ready. Why request and grant and not ready? Let us look at this situation. See, we had request, look at this cycle, we had request, we had grant, and we had not ready, right. So, address has to be held. Again look here, request is high, grant is high, ready is not yet high. So, we must still hold the address, right. Now, look what happens here, request is high, grant is high, but ready is also high, right. So, now that ready is high, we can take the address out. Clear? In the next cycle, you see address has been taken away, right. So, it is with this observation that let us say that verification engineer writes that request and grant and not ready. So, what is the verification engineer trying to do? She is trying to express this as the characterizing sequence for the address cycle. She is trying to characterize the address cycle with this predicate, request and grant and not ready, right. This is a problem because this condition can be true in other places also. Now see, look at this is the same transaction, look at this cycle. In this cycle we have request, we have grant, but ready is lowered, right. But now see, what does the data, what does the bus contain? It contains data, it does not contain the address, right. In this cycle it is containing data. So therefore this data does not have to be held for the next cycle, right. There is no need to hold the data for the next cycle. So this is part of the data cycle, and this property has confused between the address cycle and the data cycle. It is true that every address cycle will satisfy this property, can satisfy this property, but it is also true that this can be satisfied in other places also, like in the data cycle. Now what does this tell us? This tells us that the protocol has certain states. Address cycle is one state of the protocol, data cycle is another state of the protocol. Now without the state, we are trying to write the property purely in terms of sequences, and that makes it very difficult to properly express that. There is however a way of expressing this particular property, and you will see how complex it becomes. So we want to check this property on the address cycles. So we write it like this, that request and grant and not ready and not $fell ready. Now what is $fell ready? Fell ready is $fell ready is the opposite of $rose. Okay, $fell is the opposite of $rose. So now this is being used to distinguish between these two scenarios. So let us see, where did we have $fell ready? So see here in this cycle, this point we have $fell ready. Why? Because ready was high in the previous cycle, ready is low here. So this is $fell ready holds here, right. Now if $fell ready holds here, then we argue then this is a data cycle, this is not the address cycle, right. So our property is revised to say that request and grant are not ready and not $fell ready. Then if X is the address, then that address must be there in the next cycle also. Now see how complicated things are becoming, and this is a simple protocol, right. The whole problem is that we do not have state. So again you see, when we write the third property, each data cycle is of unit duration. How do we express data cycle? So again we try to write data cycle as just we saw just now as grant and $fell ready. So this is our data cycle. So we say that if this is the characterizing predicate for data cycle, then if this holds, then in the next cycle this not of this will hold. So not of this is not grant or not of $fell ready, right. So data cycle implies #1 not data cycle, right. Now is it obvious that this actually represents data cycle? Not obvious at all, right. So now we are going to look at another style of coding these assertions. We argue that, see, if you have a state machine as a reference, things becomes much easier. So we are going to use an auxiliary state machine to capture the context and the transitions between them. We will use the state labels for coding the actual properties, which will improve the readability and reduce the coding errors. So this is the auxiliary state machine for our protocol. So we have these 5 states. Initially it is in idle, then it makes a request, if it does not have the grant, it goes into the wait state and waits until it has the grant, right. Or if from the idle state it directly gets the grant, then it is going to go here straight away. Then from here in the next cycle it floats the address and then stays in this until ready is there. Remember, the address will have to be held until you have ready. When it has ready, it goes into the data cycle, and in the data cycle again, if the request is kept high, that means another item will be read or written, right. So if request is high, then again it is going to go here, and then again it will float another address. And so this is floating address here, then reading the data, then floating address, reading the data. It can go around in this loop several times, and whenever in any of these states request is lowered, it immediately goes back to the idle state. Right. At any point of time, the master can lower the request and go back to the idle state. Right. So this is the abstract state machine of the protocol. Right. This is abstract state machine. In typical protocol descriptions, these state machines are given in the specification document. They are given because people work them out and they document that, right. Now if you use this state machine, then you can write the properties much easily. Now see that address table property can be written quite simply like this, that if state is ADDR, if the state of this machine is ADDR, and if the value in the address in the bus is X, then in the next cycle this. See, all that dollar rose, dollar fell, etc. are not there anymore, right. Simply using the state of this machine, right. Remember that this state machine is part of the specification. This is not the circuit. This is part of the specification. This is something which we are writing in addition to the property. Instead of writing only properties, we are writing this state machine and we are adding on this property using the labels of this state machine, right. And then when we write it like, you can also write it like this: single cycle data transfer. You write state equal to data, then next cycle state is not equal to data. It's simple, right. Most of the complexity of the protocol is not there in the assertion anymore. Now how do we encode the auxiliary state machine? So we can encode the auxiliary state machine inside the interface quite easily like this. Now see, this is the state encoding. We just idle, wait, init, ADDR data, and we just encode them with these states. So 3 tick B 000 means 000 is the idle state, right. 001 is wait, 010 is init, 011 is ADDR, and 100 is data, right. So these are just tick defines like macro, alright. The actual state is stored in this register, in this logic. This is the actual state. Initially we are assigning state to idle, and this is tick defined to 000. So initially state is getting 000, that is the initial state. Now let us look at any of these transitions. When we are in the idle state, so case state idle, if there is no request, if request is false, then the next state is idle. So state less equal to idle. If request is high, then we check, do we already have grant? If we have grant, then we are going to go directly to init, otherwise we will go to wait. See, if request is low, we stay in idle. If request is high, then if grant is high, we go directly to init. If grant is low, we go to wait. Right. Similarly, for all the other things, say for from wait, if you get not request, then you go back to idle. If you get request, then you look for grant. If you get grant, you go to init, otherwise you stay in wait. Right. So that's what this one says. You check request and then you check grant. If grant and request both are true, you go to init. If grant is false, you remain in wait, otherwise you return to idle. Right. So this is the state machine representation. Okay. So you express the auxiliary state machine like this in your interface, and then simply write your properties like this. Right. This is a type of coding style that we came up with. See, we have a long history of working with several companies on these assertions. Right. So when a company called Synopsys was coming up with their first languages for writing assertions, openware assertions, at that time we used to collaborate with them on building the architectural styles of these assertion IPs, and this is a style which we brought into practice, and this is now almost universally followed everywhere, that develop auxiliary state machines and write properties over that. How is this checked during simulation? During simulation, this state machine is simulated like any other state machine in your circuit, right. So during simulation, the state is updated continuously. In every cycle, this state machine reads the values of these request, grant, etc., and computes the value of the state which is saved here, right. And this variable is used in the assertion. So during the simulation, it maintains the values of state and then uses that value of state as like any other variable in the assertions. Like you have P, Q, R, request, grant, etc. So state is also a variable like that, right. It is another signal. So that is being used for checking this. The formal way of doing this, of checking assertion IPs which have state machines and properties, is more recent, and there is a very recent paper from our group which talks about how to do formal verification using these kinds of specifications, and that if you are interested, we can I can give that to you, but after we read model checking, of course, then only then it is going to make sense. You can actually use multiple factored state machines also. So instead of having one single state machine, see, often for complicated protocols, creating one state machine like this is going to be very hard, right, because there are many types of transactions. There is a, it's a, for a complex protocol, you cannot express everything as a single auxiliary state machine, but you can use many state machines. Like here we are using two state machines. One has this idle, wait, init, and this transfer, and in this transfer we have the data and address cycle, right. So you can rewrite the properties like this, that state 1 is transfer, state 2 is ADDR, then x is if x is ADDR, then in the next cycle also the address will be held, right. So it is the same properties now written with more than one state machine. The properties become slightly larger, but the state machines become simpler, right. So there is a complete tool suite that we built for which you can actually create all these auxiliary state machines and then automatically use those state machines to generate a lot of different verification aids. So there is, that's targeted for bus protocols, right. So there is another paper from our group which talks about that particular tool and its usage. So that's about what I had to present for assertions and temporal logics and the background for writing properties. So, in the course now what we have so far done is we have studied all the components of simulation based verification. We have studied how simulators work, we have seen how test benches are written, we have seen how test plans are created, and then we have seen how coverage is maintained during simulation, the different types of coverage metrics, and then we have seen how assertions are written, right. The next logical thing to do is to take a look at a case study that covers all of these topics and shows you how a modern verification environment is developed, right. After we finish that thing off, then we are going to move into formal methods of verification. That would include things like equivalence checking, formal property verification, model checking techniques, abstraction refinements, and things of that nature. Okay. Thank you.